Hello, everybody. This is Professor Jing. This week, we're going to talk about hypothesis testing. So, we're in the middle of part of the course that has to do with inference for variables of interest. So far, we talk about the point estimate and learn how interval estimate enhanced it by qualifying the magnitude of estimation error in the form of margin of error. So the result is the confidence interval. So it's an interval that with a certain confidence we believe captures the unknown parameter. We are now moving to other kinds of inference hypothesis testing this week. Here are the learning objectives for this week's lecture. Upon the completion, the student will be able to describe type 1 and 2 error, as well as writing the null hypothesis and alternative hypothesis for the research questions, as well as be able to calculate and interpret Z and T test statistic for making statistical inference, and lastly, be able to calculate and interpret the p-values. Let's start with some basic concept of hypothesis testing. The purpose of hypothesis testing is to aid the clinician, researcher, and administrator in reaching a conclusion concerning a population by examining a sample from the population. A hypothesis may be defined simply as a statement about one or more population. For example, a hospital administrator may hypothesize that the average length of stay of a patient admitted to hospital is 5 days. A public health nurse may hypothesize a particular educational program will result in improved communication between nurse and patient. Statistical hypotheses are hypotheses that are stated in such a way that they may be evaluated by appropriate statistical techniques. So there are two types of statistical hypotheses: the null hypothesis and the alternative hypothesis. The null hypothesis is how a hypothesis to be tested, and the alternative hypothesis refers to a statement of what we'll believe is true if the sample data cause us to reject the hypothesis. The null hypothesis is something referred to as an hypothesis of no difference, since it is a statement of agreement with condition presumed to be true in the population of interest. In general, the null hypothesis is set up for the express purpose of being discredited. In the testing process, the null hypothesis is either is rejected or not rejected. If null hypothesis is not rejected, we will say that the data on which the test is based on do not provide sufficient evidence to cause rejection. If the test procedure leads to a rejection, we will say that the data at hand are not compatible with the null hypothesis, but are supportive of some other hypothesis. Let's look at an example and then formulate a hypothesis for it. So the example is there's a recent study that estimates 20% of all the college students in the United States smoke. The head of health service at Good Health University, GU, suspects that the proportion of the smoker may be lower at GU. In hopes of confirming her claim, the head of health services chose a random sample of 400 Good Health students and finds 70 of them are smokers. The null hypothesis proportion of smoker at Good Health is 0.2. Basically, it says that nothing special going on at GU. The proportion of smoker, there is no different from the proportion in the entire country. This claim is challenged by the head of health services, who suspected that the proportion of smokers at good health is lower. The alternative hypothesis is the proportion of smokers at good health is less than 0.2. In hypothesis testing, we select a critical value from distribution. This is done by the first determining that what is called the level of significance, denoted alpha. What we are doing here is draw a line at extreme values. The level of significance is the probability that we reject a null hypothesis when an actual true, and it's also called the type 1 error rate. Because alpha is a probability, it ranges between 0 and 1. The most common used value for the medical literature for alpha is 0.05 or 5%. Thus, if the investigator selects alpha equal to 0.05, then they're allowing a 5% probability of incorrectly rejecting the null hypothesis in favor of alternatives when a null hypothesis is in fact true. Depending on the circumstances, one might choose use a level of significance of 1% or 10%. For example, if an investigator wanted to reject a null hypothesis only if there are even stronger evidence that ensure with alpha equal to 0.05, they could choose a 0.01 as their level of significance. The typical values for alpha are 0.01, 0.05, and 0.10, with alpha equal to 0.05 is the most commonly used value. The left table summarizes the 4 possible results which can be obtained from a hypothesis test. Notice the row represents the decision made by hypothesis test, and the column represents the truth in reality. Although the truth is unknown in practice, or we would not be concluding the test, we know it must be the case that either the null hypothesis is true or the null hypothesis is false. It is also the case that either decision we made in a hypothesis test can result in an incorrect conclusion. A type 1 error occurs when we reject null hypothesis. In fact, null hypothesis is true. In this case, we mistakenly reject a true null hypothesis. The type 2 error occurs when we fail to reject null hypothesis, when in fact null hypothesis is false. In this case, we fail to reject a false null hypothesis. When our significance level is 5%, we're saying that we will allow ourselves to make a type 1 error less than 5% of the time. In the long run, if we repeated the process 5% of the time, we'll find that a p-value is less than 0.05 when in fact the null hypothesis was true. In this case, our data represent a rare occasion when it is unlikely to happen, but is still possible. For example, suppose we toss a coin 10 times and obtain 10 heads. This is unlikely for a fair coin, but it is not impossible. We might conclude that the coin is unfair when, in fact, we just simply saw a very rare event for this fair coin. Our testing procedure controls for the type 1 error when we set the predetermined value for the significant level. Notice that these probabilities are conditional probability. This is one more reason why conditional probability is an important concept in statistics. Unfortunately, calculating the probability of type 2 error requires us to know the truth about the population. In practice, we can only calculate this probability using a series of what-if calculation, which depends upon the type of the problem. The textbook did a great job breaking the process of hypothesis testing into 10 steps procedure. Step 1 is data. The nature of data that form the basis of testing procedures must be understood. Since this determines the particular test to be employed, whether the data consists of counts or measurements must be determined. Step 2, assumptions. As we learned in the chapter on estimation, different assumptions lead to modifications of confidence interval. We have seen some important assumptions about the normality of the population distribution, equality of variance, and independence of samples. Step 3 is to form null and alternative hypotheses. Here are some rules of thumb for deciding what statement goes in the null hypothesis and what statement goes in the alternative hypothesis. Suppose that we want to answer the question, can we conclude that a certain population mean is not 50? The null hypothesis mu is equal to 50, and our alternative mu is not equal to 50. So suppose we want to know if we can conclude that the population mean is greater than 50. Our hypothesis are mu is equal to or less than 50, and our alternative is mu is greater than 50. It should be pointed out that neither hypothesis testing nor statistical inference in general leads to the proof of hypothesis. It merely indicates whether the hypothesis is supported or not supported by the available data. When we fail to reject a null hypothesis, therefore, we do not say that it is true, but that could be true. When we speak of accepting the null hypothesis, we have limitation in mind and do not wish to convey the idea that accepting implied proofs. Step 4, the test statistic is some statistic that may be computed from the data of the sample. As a rule, there are many possible values that the test statistic may assume. The particular value observed depending on the particular sample drawing. As we will see, the test statistic serves as a decision maker, since the decision to reject or not to reject a null hypothesis depends on the magnitude of the test statistic. A general formula for test statistic is provided here. Step 5. It has been pointed out that the key to statistical inference is the sampling distribution. We are reminded of this again when it becomes necessary to specify the probability distribution of test statistics. Step 6. The decision rule tells us to reject the null hypothesis if the value of the test statistics that we compute from our sample is one of the value in the rejected region, and to not reject the null hypothesis if the computed value of the test statistic is one of the value in the non-rejected region. The decision as to which value go into the rejected region and which one go into the non-rejected region is made on the basis of desired value or level of significance designated by alpha, which we have discussed alpha in the previous slide. Step 7, from the data obtained in the sample, we computed a value of test statistic and compare with the rejected and non-rejected region that we have already been specified. We can calculate it using the tables or online calculator depending on the specific type of the distribution. Many computer software such as SPSS and SAS can calculate it for you. Step 8. The statistical decision consists of rejecting or of non-rejecting null hypothesis. It is rejected if the computed value of the tested statistic fall in the rejected region, and it is not rejected if the computed value of the test statistic fall in the non-rejected region. Step 9. If the null hypothesis is rejected, we conclude that the alternative hypothesis is true. If the null hypothesis is not rejected, we conclude that the null hypothesis may be true. The p-value is the number that tells us how unusual our sample results are, given that the null hypothesis is true. A p-value indicating that the sample results are not likely to have occurred. If the null hypothesis is true, provides the justification for doubting the truth of null hypothesis. Step 10. A p-value is a probability that the computed value of a test statistic is at least as extreme as the specified value of the test statistic when the null hypothesis is true. Thus, the p-value is the smallest value of alpha for which we can reject a null hypothesis. We emphasize that when the null hypothesis is not rejected, one should not say that the null hypothesis is accepted. We should say that the null hypothesis is not rejected. We avoid using word accepted in the case because it may have committed a type 2 error, since frequently the probability of committing a type 2 error can be quite high. We do not wish to commit ourselves to accepting the null hypothesis. We consider the testing of hypotheses about population mean under 3 different conditions. First, when sampling is from a normally distributed population of value with no variance. Second, when sampling is from a normally distributed population with unknown variance. And third, when sampling is from population that is not normally distributed. Although the theory for conditions 1 and 2 depends on normally distributed populations, it is common practice to make use of theory when relevant populations are only approximately normally distributed. This is satisfactory as long as the departure from normality is not dramatic. Let's see an example, and I will walk you through the steps of hypothesis testing for a single population mean. Based on our knowledge of hypothesis testing, we reply that they can conclude that the mean age is different from 30 if they can reject the null hypothesis that the mean is equal to 30. Let us use the 10 steps hypothesis testing procedure given in the previous section to help the researcher reach a conclusion. The data available to researchers are the age of a simple random sample of 10 individuals drawn from a population of interest. From this sample, a mean of x bar is 27 has been computed. Step 2, it is assumed that the sample comes from a population whose age are approximately normally distributed. Let us also assume that the population has a null variance of sigma square is 20. Step 3, the null hypothesis of mean age of the population is equal to 30, and the alternative is the mean of age of population is not equal to 30. Step 4, Since we are testing hypothesis about a population mean, um, since we assume that the population is normally distributed, and since population variance is known, our test statistic can be computed based on the formula provided in the previous slide. Step 5. Based on our knowledge of sampling distribution and normal distribution, we know that the test statistics is normally distributed with a mean of 0 and variance of 1. If the null hypothesis is true, there are many possible values of test statistics that the present situation can generate, one for every possible sample of size 10 that can be drawn from the population. Since we draw only one sample, we have only one of those possible values on which to base a decision. Step 6. We must now specify the rejection and non-rejection regions. We can begin by asking ourselves what magnitude of values of the test statistic will cause rejection of null hypothesis. If the null hypothesis is false, it may also either because the population mean is less than 30 or because the population mean is greater than 30. Therefore, either sufficiently small values or sufficiently large values of test statistic will cause rejection of null hypothesis. We want those extreme values to be constitute the rejection region. How extreme must a possible value of the test statistic to be to qualify for the reject region? The answer depends on the significant level we choose. That is, the size of the probability of committing a type 1 error. Let us say that we want the probability of rejecting a true null hypothesis to be alpha 0.5. Since our rejection region consists of two parts, sufficiently small values and sufficiently large values of the test statistic. Part of alpha will have to be associated with large value, and part of it will be associated with small values. It is reasonable that we should divide alpha equally and let alpha divided by 2 is equal to 0.025 be associated with small values, and let alpha divided by 2 equal to 0.25 to be associated with the large values. We look in the body of appendix table D until we find 0.975 or its closest value, and read the corresponding marginal entry to obtain our z value. In the present example of value of z is 1.96, similar reasoning will lead us to find negative 1.96 as the value of the test statistic so small that when the null hypothesis is true, the probability of obtaining a value this small or smaller is 0.025. Step 7. From our sample, we compute the test statistics to be negative 2.12. Step 8. Based on the decision rule, we're able to reject the null hypothesis since negative 2.12 is in the rejected region. We can say that the computed value of the test statistic is significant at the 0.05 level. Step 9, we conclude that m is not equal to 30, and let our administrative or clinical action to be accordance with this conclusion. Step 10, instead of saying that an observed value of test statistic is significant or is not significant, most writers in the research literature prefer to report the exact probability of getting a value as extreme as or more extreme than that observed if the null hypothesis is true. In the present instance, these writers will give the computed value of the test statistics along with the statement p is equal to 0.340. The statement of p is equal to 0.340 means the probability of getting a value as extreme as 2.12 in either direction when the null hypothesis is true is 0.0340. The value of 0.34 is obtained from Appendix Table D and is the probability of observing a z-value that is greater or less than 2.12 or a z-value that's less than or equal to negative 2.12 when the null hypothesis is true. That is, when null hypothesis is true, the probability of obtaining a value of z as large as or larger than 2.12 is 0.17, and the probability of observing a value of z as small as or smaller than negative 2.12 is 0.17. The probability of 1 or the others of those events occurred when no hypothesis is true is equal to the sum of two individual probability, and hence in the present example we say that the p-value is equal to 0.17 plus 0.17 is equal to 0.034. A general rule worth remembering then is that if the p-value is less than or equal to alpha, we reject the null hypothesis. If the p-value is greater than alpha, we do not reject the null hypothesis. In the last example, we were able to reject the null hypothesis because the computed value of the test statistic fall in the reject region. Let us see how we might have arrived at this conclusion by using a confidence interval. The 95% confidence interval for mu is 24.23 and 29.77. Since this confidence interval does not include 30, then we say 30 is not a candidate for the mean we're estimating, and therefore mu is not equal to 30 and no hypothesis is rejected. This is the same conclusion reached by the mean of hypothesis testing procedure. The previous example is an example of two-sided test because the reject region is split between two sides or tails of the distribution of the test statistics. A hypothesis test may be one-sided, in which case all the rejection region is in one or the other tails of the distribution. Whether a one-sided or two-sided test is used depends on the nature of the question being asked by the researcher. Suppose instead of asking if they could conclude that mu is not equal to 30, the researcher had asked, can we conclude that mu is less than 30? To this question, we will reply that they can so conclude if they can reject the null hypothesis that mu is equal or greater than 30. As we have already noted, the population variance is usually unknown in actual situations involving statistical inference about a population mean. When sampling is from an approximately normal distribution with an unknown variance, the test statistics for testing mu is equal to mu 0 follow a t-test with n-1 degree of freedom. If, as is frequently the case, the sample on which we base our hypothesis test about a population mean comes from a population that is not normally distributed, we may, if our sample is large, takes advantage the central limit theorem using the z as the test statistic. If The population standard deviation is not known. The usual practice is to use the sample standard deviation as an estimate. The test statistic for hypothesis testing becomes z equal to x bar minus mu subscribed 0 divided by s over square root of n. You can see that we replace sigma by s, which is the sample standard deviation. Let's work on this case and study by yourself. Once you're done, move on to the next slide to see the solution. I just want to point out step 10, how to find the p-value. As shown in the table D, the area to the right of 2.78 is less than 0.05. The area to the right of 1.645. The hypothesis testing involving the differences between two population means is most frequently employed to determine whether or not it is reasonable to conclude that the two population means are unequal. In such cases, one or the other of the following hypotheses may be formulated. It is possible, however, to test the hypothesis that the difference is equal to, greater than, or equal to, or less than, or equal to some value other than 0. When each of two independent simple random samples has been drawn from a normally distributed population with no variance, the test statistic is calculated as the formula shown on the left. When the population variances are unknown but assumed to be equal, we recall from chapter 6 that it is appropriate to pool the sample variance by calculating the pooled variance. And we use the pool variance to calculate the test statistic. One thing worth mentioning is the degree of freedom, which is n1 plus n2 minus 2. When the population variance are unknown, but assuming they are unequal, then the calculation of test statistics become more complicated. However, the good news is that we don't need to know how to calculate it in this course, as most computer software can do it for you. What I want you to know is check the two population variances and understand the test statistic is calculated differently depending on whether they're equal or not. When sampling is from the populations that are not normally distributed, the result of central limit theorem may employ if the sample size are large. Remember, we talked about if we have sample size that is more than 30, we say that the sample size is large. So to calculate the test statistics, you can use the formula shown as below. It is the time to exercise your knowledge, work on this case study by yourself, and compare your result with mine on the next slide. Here are the solutions. I hope you have the same conclusion. Feel free to let me know if you still have any questions. In public health and medicine fields, lots of time we use paired sample to eliminate the maximum number of sources of extraneous variation by making the pairs similar with respect to as many variables as possible. Examples of paired samples include: first, pre-test, post-test samples in which a factor is measured before and after an intervention. Second, crossover trials in which individuals are randomized to two treatments, and then the same individuals are crossed over to alternative treatment. Third, matched sample in which individuals are matched on personal characteristics such as age and sex. The fourth is duplicate measures on the same biological samples. And the last is any circumstances in which each sample points in one sample is uniquely matched to data points in the second sample. When we have paired sample, we use DI, which is the difference between pair of observations as the variable of interest. We no longer perform our analysis with individual observations. The test statistics for testing hypotheses about the population mean difference, mu d, can be calculated using the formula shown on this slide. So d bar is the sample mean difference. Mu d0 is the hypothesized population mean difference. SD bar is calculated as SD divided by the square root of n, which n is the number of sample difference, and SD is the standard deviation of sample difference. Notice that the test statistic has an n-1 degree of freedom. Now let's pause here and try to solve this problem by yourself. Once you're done, see the solutions on the next slide. For step 1, we need to further prepare the data by calculating the difference between pre and post percentage. Testing hypothesis about population proportion is carried out in much the same way as for mean and when the conditions necessary for using the normal curve are met. One-sided or two-sided tests may be made depending on the question being asked. When a sample is sufficiently large, the test statistic is calculated using the formula shown on this slide. When the null is true, the test statistic follow a standard normal distribution. Let's pause here. It's time to exercise your knowledge. See the solution on the next slide. You can pause here again to compare your answer to my answers on this slide. If you have any questions, you can feel free to email me. When the null hypothesis to be tested is P1 minus P2 is equal to 0, we are hypothesizing that the two population proportions are equal. We use this as justification for combining the result of the two samples to come up with a pool estimate of the hypothesized common proportion. After you have pool estimate the hypothesis common proportion, you will need to calculate the standard error of pooled common proportion. Once you have the standard error, you are applying the third formula on this slide to calculate the test statistics. Sometimes epidemiologists would like to know if a sample variance is larger or smaller than a certain number. If those cases when the sample is drawn from a normally distributed population, the test statistic follows a chi-square distribution. For testing hypotheses about a population variance can be calculated using the formula shown on this slide. Decisions regarding the comparability of two population variances are usually based on the variance ratio test, which is a test of null hypothesis that two population variances are equal. When we test the hypothesis that two variants are equal, we are in fact testing the hypothesis that their ratio is equal to 1. The test statistic is designated as VR. It is a simple calculation such that S1 square divided by S2 square, it follows a F distribution with N1 minus 1 as the numerator degree of freedom and N2 minus 1 as the denominator degree of freedom. You are not required to calculate it in this course. And that's all I have for this week. Do not hesitate to contact me if you have any questions. Thank you.